Okay. So let's go ahead and get ourselves started here. So if we can't finish up chapter 1, and get ourselves a good, healthy start on chapter 2. So this look familiar? How where we left off? Roughly. We're kind of hitting the last home stretch of chapter 1. So we're looking at some of the philosophical components of science still. So one of them, we talked a lot about, some of the different approaches and things like that. We talked about how to set up an experiment. That's interesting. I wonder what happened to that. Well, they're supposed to be there. It is. So, so now what we want to do is we want to take a look at, so we looked at the experiment, right? Setting up a control experiment, setting up an experimental group, right? To have a controlled experiment, to use the wheat field fertilizer example, right? Last time. A couple of other things we want to just take a quick look at in biology is something that really does set the biology and science in general apart from its counterparts, right? So when you're looking at the different fields of thought and intellectual disciplines, theology, philosophy, we talked about, right? Science is a kind of a different creature. One of the things that sets science apart is its approach. Its approach is reductionist. Now, what reductionist basically means is you take something big, right? So like a big complex process, and you break it down into a smaller part. And now you can think of it sort of like eating, right? So you don't basically take, the quadruple stack burger, the heart attack on a bun, with extra clogged arteries on the side. You don't just shove that thing down all at once, do you? You take it one bite at a time. That's a reductionist approach. You realize that the problem you have on your hands here is too big for you to take in all at once. And so what you do is you basically make the correct logical assumption, which is if I solve one little piece of this at a time, and then I put all those little solved solutions together, then what I'll get is the full picture. Okay. By the way, if that sounds very familiar to you, you use basically the exact same logical approach when you do a puzzle, right? So you don't just take all the pieces and just mash them all together and hope you get it right. That's going to be impossible, right? To do that. So what do? We go one piece at a time, right? So that's a reductionist approach. If I understand how this one piece fits in the overall plan, then, and I do that again and again and again, I can start putting pieces together, then eventually I'm going to solve the problem. And that's exactly what science does. Now, how does this differ from things like theology or philosophy, the intellectual disciplines? Well, the other intellectual disciplines are reductionists. They don't take big problems and make them small. They take small problems and make them big, right? So that's kind of the way they think. They think expansively, right? So they take a look at one small thing and then they kind of blow it up into its greater sort of universal meaning or whatever like that, right? And that's kind of what makes them cool, is because they kind of have a way of blowing your mind, because you're looking at a big thing, like you kind of blow it up and it's like, wow, I never really saw it like on that scale before, right? So, and scientists don't do that. Scientists basically go the opposite direction. And that's because they're trying to solve a problem in a very discrete sort of a way. So the other thing is also systems biology. For instance, this is an actually entire field of biology, but it is kind of a philosophical approach. This is essentially when you're taking a look at biology as sort of an amalgam, if you will, or a summation of all those emergent properties. And we talked about all those emergent properties associated with going from one level up to the next. So going from like the atomic level up to the molecular level, from molecular up to the organelle level, from the organelle to the cell. So every time you move up, you kind of acquire an entirely new spectrum of capacities, those emergent properties. And when you're in biology and you study those, because they're kind of fascinating and they're somewhat mysterious because they're not additive, so they don't make sense to us. Our brains are very additive. That level of understanding, that kind of philosophical approach is what's called systems biology. So the idea is that oftentimes you get more than you think. When you add 2 + 2 together, it's actually not 4. It's actually more than 4, right? And so that's kind of what the emergent properties is. And that's oftentimes what systems biology tries to do, is tries to understand, well, wait a minute, in a universe where 2 + 2 = 4, then how do we get more than 4? Right. And that's kind of what systems biology goes into. Models. This is an important one, right? Because when we take a look at science and we're taking a look at, forming some sort of a question, we're trying to study some sort of a phenomena, some sort of natural phenomenon. And we make a hypothesis, right? Which is kind of our best answer to the question we ask. A lot of times, a hypothesis is just a single answer for a single question. But what if what you're looking at is a little bit bigger than all of that? There's like a lot of different moving parts to it. Like you're trying to basically tell a story, right? Matter of fact, if you've ever watched court TV, defense attorneys will do this a lot of times, right? They'll kind of create a theory, right? A defensive theory, where they basically try to use the evidence to suggest a series of events that obviously favors their client, right? And then what they're saying is that this narrative that we just created, this story that we just created, the way we think it happened benefits my client, but then the data supports that, right? And so that's kind of like what a model is. A model is actually usually many hypotheses that are woven together in a narrative. It's a story. That's what a model is. But the important thing about a model is this is our scientific story of how we think it works. Now, it may or may not be accurate, right? So what a model actually represents for us is actually something we can test. So we can actually form experiments against our model. So if our model is accurate, then when we do experiments, our data should be consistent with our model, right? For instance, if you did the crime, then we should see evidence of you being there, right? Like, for instance, DNA evidence. So if our model is correct and we think you were there, then our data, that is our search for you essentially at the crime site, should be consistent with you being there. If we find nothing of you there, is that consistent with our model? No. If we find your DNA there, is that consistent with our model? Yeah. Does that necessarily mean that you did anything wrong? Not necessarily, right? It just means you were there. And if you were lying about that, it kind of obviously raises some red flags. What were you lying about? What'd you do? What you covered up, right? So we jump to natural suspicion. By the way, scientists don't jump to suspicion. They're not supposed to. We do, actually. In reality, we do. But in practicality, in sort of purest sense, we shouldn't. We should let the data lead us, not let us lead the data. Okay? When we jump to suspicions, that's us leading the data. So ultimately then, oftentimes we'll use models. This is our story of how we think things are. And the reason why these are important is because it helps us to sort of imagine a little bit, because we're very visual, we're very narrative, right? I mean, that's kind of the way we learn. We tell each other stories, and that's how we learn from each other. So when we have this narrative or this model, it makes sense to us, because now all of a sudden we can see all these different pieces and how they fit together in the drama that we're trying to solve. In this case, the drama is not exciting. It's not like anybody's being killed. It's like a biological mechanism, right? That's high drama for a researcher, right? That's exciting for us. So when you're kind of trying to put all that together and figure out how things work, that's your model, that's your drama. Now, just because you see a lot of this, right? And science does a lot of this. We do it for ourselves so we can better imagine how things could have been, or how things are, how they work. And then the idea is the models themselves, because they are hypotheses, are testable. And the nice thing about this is because you've got a series, not just one hypothesis, but a bunch of hypotheses in there, you can do experiments on different parts of your model. So like if I've got this long series of events that happens, here's first A happens, and then B, and then C, and then D, and then E, and then so forth. then I can do experiments on the first event. And some of my experiments may not be consistent with the model. Now, does that mean the entire model is out the window? No. It just means that one particular piece of the model you're still kind of working on. Okay, so you just kind of fine tune that a little bit. The rest of the model may be fine. And the rest of the model has other questions and other experiments associated with it. So a model represents kind of like a really big like candy store of hypotheses for a researcher, where they can ask lots of questions, do lots of experiments, and try to figure a lot of things out. Now, the important thing is, and this is always one thing, because we love a good story, this is always the case, there's two things that scientists will do when they do modeling. First of all, this is where we separate fiction from potentially fact, or a search for fact, is in its testability. When you're looking at a scientist talking about a model, they're not just talking about a story, they're talking about a series of hypotheses that they themselves can test. So what does that mean? That means that there's going to be a lot of models out there that are not horribly testable. And what that means then is an untestable model are mythology. They're stories, and that's it. Right? Now, those are fighting words in some corners, right? Because a lot of people love their models. But here's the thing, though, and this is kind of what I want you to be critical about, right? So being critical is not a bad thing. That means you're being objective and you're asking questions. You're not interested in, you're not interested in opinion when you're a scientist. You're interested in how things work. There is objective truth. You're not a postmodernist if you're a scientist, okay? Because if you're a postmodernist, guess what? In your universe, 2 + 2 doesn't equal 4. It equals whatever you think it is, which honestly would be absolute catastrophe and chaos in the universe. So that's just your perspective from a scientific point of view. But here's the thing. We use models in 2 different ways. Models for ourselves as a series of hypotheses that we can test and try to understand the nuts and bolts of how things work. And that is the healthiest way of using a model. However, there's another way, a little bit of a looser way that we use models, and that is as a way to educate and communicate. And so oftentimes we will kind of educate and communicate what we think is our current knowledge or our current ideas about what's going on. But they are, well, propaganda is a bit of a strong word, because that suggests that you're intentionally trying to deceive somebody, and that's not necessarily the case. But you're trying to educate folks and you create this rosy picture, and that may or may not have gone down that way at all, because your model that you're trying to communicate and teach people about is based on an ongoing shifting body of knowledge that's constantly being changed and morphed as we learn more information. Here's a good example. It always makes me chuckle whenever I talk to some individuals, and from an evolutionary point of view, I'm a molecular guy, right? So that's like the bedrock piece of it. But it always kind of makes me chuckle when I go to like a museum of natural history or something like that, which honestly, I hate museums of natural history. But when you look at that, they have these pretty pictures, don't they? Like these dinosaurs kind of crawling around all over the place, and they got these pretty little trees. And I kind of look at those pictures, and I kind of chuckle to myself, because I'm like, yeah, we don't know half of that, actually. I mean, there's some things we do know. We have obviously discovered fossils of the dinosaur that they're showing. That's true, right? We have been able to figure out maybe some things of some ways that it might have looked, right? And that's true. We have discovered maybe some fossils of cycads of that day. So we have an idea of what the plant looks like, and that's true. But all the rest of it is all fiction. But guess what? It's all drawn as if they took a photograph from the Triassic. And not only that, but listen to and this is what I have, this is where I kind of have a problem, because it creates a delusion is what it does. And so we can't get past that and learn more because we run into this delusion. But listen to the people doing the tour guide, right? The tour guide guy. They're saying like, this is what it looked like. Really? How old are you now? I mean, yeah, I understand the cycad. I've seen cycad fossils, but have you? Right? I've seen the dinosaurs fossils, and that's true. But have you? Right? So there's a lot of assumptions going into building the picture that we draw, that is the model, of how we think the dinosaur looks based on some of the things we found. But a lot of those are not testable because we're not there. Nobody has any clue what color they were. None whatsoever at all. They could have been fluorescent pink. They could have glowed in the dark. Nobody knows. But what color are they always drawn as? Green, gray, right? Something boring and drab. Now, is that what color they were? No. Did we find dinosaur skin that's that colored? No. So how do we know it was green? At some point, you kind of have to make it up, right? So what you're doing is you're hypothesizing. At that point, as a model, you're saying, well, we're hypothesizing that it's green because what? Because we don't see any fluorescent pink lizards or reptiles today. Fine, but that doesn't necessarily mean they weren't fluorescent pink, right? I mean, if mutation is happening, they could have mutated into green instead of fluorescent pink. None of that would have been preserved in the fossil record, but that is a hypothesis. Your hypothesis is that these guys were green or gray. But the problem is when you go to a museum of natural history, they don't propose it that way, do they? They propose it as like, we've been there. We took a photo of this guy running across this cycad forest after this poor little mammal. Really? It's not as well known as all that, right? This is the problem I have. In the name of education, they've basically skewed what we actually know well and what we don't know well. And for like just general people, it's very confusing because now all of a sudden they're like, well, wait a minute. How much of what you're telling me is like a little over embellished? And how much do you actually know? I mean, to the point where it feels like they're lying to you. And I would argue they are, because they're not being truthful about what we do and don't know, because it's really actually fascinating what we do and we don't know, because that's where we start to learn some things. Now, some of those museums are starting to change. They're being a little bit more honest about it. They're still educating, by the way. They're still drawing, that's fine. And they're still saying, this is what we think might've happened, but, you know, so you're seeing more of that. And because a lot of people have noticed that because of that, that sort of over polished version of things, it's not helping anybody. It's actually holding us back. And that's kind of the reason why I keep talking about this, is because the way you approach this can actually hold you back and send you backwards in your knowledge. Hello, Dark Ages, instead of forwards. Okay. And that's why I hate museums of natural history. So, because most of them, you know, and if you ask any question, they get really offended. Like, since when in science have we been taught not to ask questions, right? Since when in science have we been taught to be offended when somebody asks us questions? Last time I checked, questioning is the bedrock of science. That's what you do. You ask questions for a living. If you can't handle questions, you're probably in the wrong discipline, right? There's some other disciplines that don't handle questions very well, but not this one. That's what this one's formed on, okay? That's, by the way, that's my litmus test. You remember when I said I have no problem poking the bear? You know why I poke the bear? I poke my colleague bears all the time. You know why? Not to be a jerk, a little bit, but I poke them because I want to know where they are. It's like, you know, if I ask you a question, have you sold out? Have you turned this from science into something else? Or are you still legit? Are you still a scientist? Or have you become a used car salesman now? Where are you? Those are strong fighting words. But like I said, first thing out of my mouth, right? First day, I'm a science purist. That's what's gotten us here. So those folks who are not purists are usually the ones holding us back. Fighting words, and all recorded. Love it. Won't back away from it. So scientific theory. Now, here's the thing, right? So with scientific theory, one of the things you want to make sure that you understand is that, like, when we're talking about theories in science, it's not like, you know, court TV where you're talking about a theory. It's just like a Hail Mary story that you're just trying to hope and pray is true. In a scientific theory, remember, this is something that has been supported by a body of evidence. So that's what we are as a scientific theory. So when a scientist is talking about a theory, it's not like a theory like most people think. I mean, this is something that has been established and it has been supported, right? So we, technically speaking, could it be something else? Could we be a little wrong? Probably, but the more experiments we do that are consistent with our theory, the less likely of us being wrong becomes, right? So we become more likely to be correct, okay? It's like the blue sky idea, right? After one observation, could you be incorrect? Could you have seen it wrong? Yeah, sure, right? But after multiple observations, multiple experiments where all the results are all true and consistent with your hypothesis, that is that the sky is blue, guess what? We're pretty comfortable with the sky is blue now, aren't we? Right, so that's kind of the same idea. So a theory is an idea that is supported by experimental evidence. And that's the reason why we have to do experimental evidence. Why it has to be testable. Because what is a theory that is not supported by experimental evidence? What is that? It's an idea, right? It's more kind of a theory without evidence is not science. It starts to move more toward philosophical and theological direction, right? Because they also have theories, by the way, right? That's not, theory is not like a thing for just scientists. There's theological theories, there's philosophical theories, but those theories typically are not testable, at least in the way science is, right? And so it's kind of a different thing. It represents sort of a different way of looking at things. But if you don't have evidence, then you're starting to move to philosophical and theological areas. And that's tough, right? Because that's always the big struggle with studies of origins, is because you're going back into eras where you can't do discrete tests, and you're limited because you can't travel back in time, right? And step on the butterfly, so to speak, right? Which then turns us into like these little guild creatures, apparently. I forget what movie that was. It was a great movie. It was interesting, but not Waterworld. It was some other. It was like a movie where we figured out how to go back in time, and it was like a travel industry, like space thing, right? Like, if you pay me enough money, I'll shoot you up into space. It was like, if you pay me enough money, we'll go back in time. We've got this hunt set up. So we've got this T-Rex that we know is in the fossil record. So it dies. So if we kill him, then it's not going to disturb the timeline. And so the idea is you take this T-Rex that was already in the fossil record and you go back in time, and they got like some little tricked out sidewalk, like holocraft, like a holo sidewalk kind of a thing where you walk on it. And of course the T-Rex rises up and you shoot them, right? So it's like one of those big game safari sorts of things. And then you're supposed to come back and feel good about yourself because you killed the T-Rex. Right? And it doesn't matter, right? Because the T-Rex is already dead. It was already in the fossil record. So if you kill something that was already supposed to be dead, you're not changing the timeline. But then some bozo fell off the sidewalk, stepped on a butterfly, and then it started changing the line of evolution. So it's like every now and then, like, reality present would update itself, and evolutionary change. Like, we had crazy monkeys running all over the place, and the plants were taking over the world, and then eventually we turned into some sort of quasi-amphibian thing, which was always fascinating. But that was just interesting just to watch that. But that's what I meant by don't step on the butterfly. Can't remember. Has anybody seen that movie? I have a lot of these plots in my head where, like, movies I've seen or books I've read, I'm like, what is that? I can't remember what it was for the life of me, but it's like, I've got it there. So if there's an app where I can just lay out the plot and it can give me the name of the movie, let me know, because I've got questions. But right, so the idea then is a theory is a little bit different depending on different disciplines. Then of course in science we have basically our methodology, right? So that's something that also sets us out, that's distinct. So reductionism is a distinct characteristic of science that separates us from theology and philosophy. Our scientific method also sets us apart from the other two as well, right? As a matter of fact, a lot of people would be like, oh, well, the others have a method too, right? No, they don't. No, they don't. Science is the one that pulled this together. The other disciplines kind of started stealing it from us because they realized how useful it was. Okay, so it was ours. Got stolen from us. No, but it's a good thing, right? Because it helps you to sort of logically frame your study so that what you find out, the information you find out, is more rigorous and has more impact. Okay, because right, anybody can have an opinion, right? But only people who are right have facts. Right? So opinions are cheap, truth costs you. Okay. And so that's kind of what we have here. So you can have an opinion theologically or philosophically, right? So those are easy to come by. Anybody can do that, but you have to have a little bit more rigor if you're trying to actually discover, well, what is the actual story, right? So that's kind of like an important piece, our methodology. So these are some of the unifying themes of biology. These are overall things that we see in biology itself that pull them together. Now, I'm not going to go into a lot of depth on these for the most part, because we have entire chapters on these, or we'll talk a lot about these throughout the semester. So obviously one is the cell theory. So basically this is the bedrock or the foundation of all living things. Chapter, I believe it is 4. These are our cell chapters. So we'll have an entire chapter working on cells. The molecular basis of inheritance. This is another one. So these are the last chapters toward the end of the semester. We're talking about DNA replication, transcription, translation, basically how you go about organizing your body, right? So one of the things we want to do as we go throughout the semester is basically pretend like we're trying to build a biological organism. Now, the question is, in order to build a biological organism, we have to sort of lay down some of the road rules, what we can and can't do. And we have to start inventorying our supplies, right? So what do we have? What materials do we have in order to build with? And how do I want to assemble these materials? Okay, so that's something we want to do. And that's kind of like the first couple of chapters we have. But when you take a look at what's called a molecular basis of inheritance, we all circle and sort of focus our studies around DNA. Now, remember, I said that like evolution was a genetic thing, right? At its heart, which is the reason why genetics is at the epicenter of genetics. I mean, of the biology. Why? Here's the reason why. We have 2 different terms that I want to define for you now, and then we'll touch bases on these guys again when we kind of move a little further down. So the first thing is the gene, right? So a gene essentially is, in this case, they say a discrete unit of information. It is true. It is a discrete unit of information, but it is specifically a discrete unit of DNA that has information associated with it. And there's a code that goes with that. We'll crack that code a little later on in some of the later chapters in the semester. But the idea is this, that every single trait in your body has information that governs how it comes out. So if you have dark hair, it's because the genes that you have all encode the information for dark hair. So everything you look like, the traits that you have, are all encoded by your genes, which is the DNA information that you have in your body that dictates how those traits come out. Now, where do you get your genes from? Your parents, right? So you get them from mom or dad. And where'd they get them from? Grandma and grandpa, right? And where'd they get them from? Great grandma and great grandpa, and so on and so forth, as far back as humanity goes, right? So that is the idea of the flow of information. It flows from generation to generation. That's heredity. That's genetics. But it comes and is housed on DNA. Now, the other term is something that I have kind of thrown around a little bit, but I haven't really defined it very well, have I? And that's the idea of a genome. And so a lot of you guys will be like, wait a minute, what's a genome exactly? Well, so a genome is defined as the complete set of instructions necessary to make you from scratch. Now, what I just defined there is what's called your own personal genome. Okay, so there's two different versions of a genome that you'll hear me refer to. So the first one is your personal genome. So I will pick on Matt just because I know Matt. Right. So Matt's genome, right? He has his own genome and I have my own genome. Our genomes are not the same, right? But his genome is basically his complete set of DNA instructions, everything to make him from scratch. So where do you find that? In the nucleus of every single one of Matt's cells. So inside every single one of his nuclei and every single cell in his body is the complete set of instructions to build Matt from scratch, from zero to another Matt, right? So we could have like hundreds and hundreds of Matts running around. Okay? So, right, and so that's his personal genome. Connor has his own genome, right? And where do we get that genome from? Parents, right? You're like, yeah, right, yeah, from our parents, right? That's the reason why my genome is not the same as Connor's, right? So that's one level of genome. So I have my own genome that I get from my family lineage. Connor has his, Matt has his, and so forth. However, there is another level of genome that kind of combines all of us, and that's called the human genome. This is the one I mentioned before. This is the one that we sequence, and that's basically all the information that exists genomically, DNA-wise in the human species. That is all 7+, I think it's up to 8 now, 8 billion of us all together, all of our genetic information, all piled up into one big pile and summed up. That's the human genome. Every scrap of information necessary in the entire human species. That's, by the way, what we sequenced about 20 or so years ago. And that's a ton of information. And not only did we sequence that for us, but we've sequenced it for many, many organisms since. And so we have a lot of DNA information. This is one of the reasons why evolution based on fossil record is a little antiquated. It's like, why in the world would you want to study relationships of stuff that have been dead for millions of years when you've got all this treasure trove of information from organisms that are alive today, and you study their relationships to each other? That's abundantly more fascinating. Not only that, by the way, all those guys that are dead had DNA too. So if you want to know their story, you have to know their DNA. So guess what? You can't really understand what's going on unless you know the genomes and how they're related to each other. So here's another big one, structure function. So structure function is basically a common theme that you're going to see all the way throughout biology, not just here, but also in AMP. You're going to see this. You're going to see this pretty much everywhere. If you take Bio 2, you're going to see this. So the structure function relationship is something that's very sensible to us. Generally speaking, the reason why I like to always start with the task of building an organism, right? Let's build an organism, is because in order to build an organism, you need two things. First of all, what are you trying to achieve? And how do you achieve it, right? You need to answer those two questions, yes? So the question with building an organism is very simple. What are you trying to achieve as an organism? Yeah, reproduction, right? Now, what do you need in order to reproduce? Think about the same list that we saw that had reproduction on it. Oh, energy, right? So all these big biological questions of life. So guess what? Though you have to answer. If you're going to build an organism, you have to come up with some sort of an answer for all of those, right? So let's take a look at the energy plan. That's great. Energy plan, you need that one. Nice. Okay, now what? How do you build an energy plan, right? What do you need to do, right? What are your functions that you need to accomplish? So oftentimes when you take a look at it from the perspective of starting with building an organism and then trying to figure out which big biological questions of life you need to answer, then that's going to have a whole laundry list of different functions you have to be able to do. If I'm going to successfully have an energy plan that's going to fuel my biology, then I need to be able to do this and 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 this. Okay, that's great. How are you going to do that? So what you did is you've defined function, yes? So you start off with function. But then now you have to figure out how to build the structure to achieve that function. Here's a good example. I'm going to give you a function. I want you to give me a structure. I want you to drive a nail into a piece of wood. What's your structure? Huh? I mean, but how are you going to do that? So your function is I have to drive this nail into wood. So what are you going to create in order to do that? It's not a trick question. Yes. A hammer. Okay. So that's one structural solution to driving the nail. Yes? You do need energy. I like that one. That's a bigger discussion, but yes, I like that one. Hang on to that one. That energy is always big because it's still the universe. Okay, let's take a look at the hammer. What's the hammer? Go ahead. Describe this to me. Draw the plans for building a hammer. This is a function, but we have no existing structures. So we're a little cheating, right? Because you know what a hammer is. You can go to Lowe's and buy one. That's cheating. There's no Lowe's. There's nothing. You have to create the hammer. So what are you going to create? How are you going to build it? Metal. Where? How? What? Just a big block of metal? Okay, for what? The handle. Okay, so you're saying the handle's made out of wood. Okay. And then what? So the head. So you're saying make the head out of wood? So a full wooden hammer? Okay. If the nail that I'm trying to strike is made out of metal, how's your structure going to work? Okay, so a rock, that's a different story, right? So a hammer was one suggestion. A rock is a completely different thing, right? That one's a little bit easier. You can grab the rock and just bang on it, right? So let's follow up with the hammer. So rock is a good one. Let's follow up with the hammer. So we've got one design of a hammer, right? So wooden handle, wooden head, right? That's a blunt force object on a metal target. Now let's go ahead. Are there more than one type of hammer? Yeah. Lay it out there. I know nothing. I don't even know what a hammer is. Never seen one before in my life. What are you thinking? What are these alternative designs? We're going to let Connor hang on to the full wooden hammer. Okay, so go ahead. Next design. A fully metal one with a what handle? With a rubber handle. Now, is it solid rubber or just coated? Like just a rubber sheet? Okay, excellent. So that's a different construction, a full metal hammer, right? Now, how successful is that going to be? Yeah, right? Any other designs? If you had a roofer on top of your house, are they up there with a hammer? What do they got going? Yeah, watch out, man. They're just like, right? I mean, there's just like, it's like an AK-47 for nails, right? Is that basically a hammer? Yeah, right? Is that the same thing as full wood? Is it the same thing as full metal? Is it doing the same thing? Yeah. Notice what we did. We all answered the same functional question, didn't we? But we all came up with different ways of going about it. So Connor is one species. Full metal hammer, Matt, is another species. The air gun is a different species. Rock is even a further species than these guys. So when you're looking at relationships, you can say all of you guys are related because you guys are like in sort of the hammer-like family, right? So maybe you're a different genus because you're all kind of like some sort of a leveraged hammer. But you can see that two of them are more related to each other than normal, right? So like the full wood and the full metal are more closely related because they're basically the same construction. They're just different materials that they're made out of, right? So these two are more closely related to each other. Further out is the air hammer, right? So that's basically the air gun. So that one is kind of further out. And then even further than that is the rock. because you're looking at something completely different. So you can see how you can sort of change the relationships between these organisms and start to create these lines of descent. If I did that, basically what I created was what's called a phylogeny, like an evolutionary tree, where full wood and full metal are more closely related to each other with a common ancestor. Right? And so you can kind of see how you can basically take just what we have now, just whatever you're made out of, and how closely similar you are structurally, morphologically. And then we say the closer you are, the more closely related you are. That's how we have all these evolutionary trees. That's how we do it for the most part. Because we say, what do we see now? And how closely related are you? And then from that, we could say, then you must have had a more recent common ancestor. It's an interesting approach, right? But always remember, and that's kind of what we work with, but always remember, we don't know what the common ancestor was. We weren't there, so we're guessing. Anything that goes further back than now is a hypothesis, right? So when you take a look at an evolutionary tree, you see basically all these organisms and how closely related they are, and that's very fascinating. But when you start to go back into the tree, back into time, it's all, we're not quite sure exactly what's going on there. We think these two share a common ancestor, but unless we have fossils to support that or something of that nature, or DNA from a fossil to support that, hello T-Rex, I'm looking at you, right? So then we don't really know exactly how the rest of the tree is working. So that's, we kind of, that gets, and the further back we get, the harder it gets to know for sure, okay? Like for instance, it could be that maybe you two, the two hammers, are not more closely related to the air gun. Maybe you guys are more closely related to the rock, right? Because you've got physical striking, because you've changed material, and now the air gun is more of an outlier, right? So you can see how you can sort of switch these up depending on what that looks like. Okay. That's actually a really, really good exercise to sort of show you how we do this process. Okay. But it's also a good exercise to show you exactly how function and structure go together. We all have the same function, yes? We all come up with different structures, yes? Because we came up with different structures, that means we're all different things. That's diversity. And then when we're kind of trying to understand the relationships between all these, that's where you start to get phylogeny and evolution and origin of species and things like that. It's like, okay, that's fine. You two are very closely related. You're very similar. So you must have been more closely related than these guys over here. And that's kind of what we're working at. That's the reason why it kind of all comes together in kind of a big ball. But structure function is something that we utilize and we look at all the time. Information processing. So basically everything goes through your DNA. So if this is your complete set of instructions, everything flows from your DNA to your cells essentially to build you. Now, the one thing I wanted to mention here, this is one of the last ideas that I have that I want to talk about, is equilibrium. Because sometimes in chemistry, you'll talk about equilibrium. And in biology, we have this idea of equilibrium. And all equilibrium is essentially at its most discrete, is when you have a chemical reaction, right? So you have reactants. So you have, molecule A and B colliding together, and they go through some chemical reaction to become C, right? Something like that. Typically in a chemistry reaction, there's a forward reaction where A and B goes to C, but there's also a reverse reaction where C kind of falls apart into A and B. So it's kind of going back and forth and back and forth and back and forth. And when there's balance between the two, that is to say that when the two rates are roughly equal, that's equilibrium. And you can think of equilibrium kind of like a placid pond, right? Like a glassy surfaced pond. Very boring, biologically speaking. In biology, we don't like equilibrium because nothing good happens with equilibrium. Only the good stuff happens when you perturb equilibrium. This is the reason why this slide is not equilibrium state, which is what it is in chemistry. It is non-equilibrium, because from this comes resolution. Why? Because if you disturb equilibrium, you have to restore equilibrium. In the process of trying to restore that equilibrium, you get resolution, which then leads to biological function. This is the reason why you jack with the system, basically, right? You jack with the system to try to achieve some particular effect. Okay, you're trying to create some sort of a biological effect. So when we see, generally speaking, these non-equilibrium states, we oftentimes will perturb them. As a matter of fact, most biological states are not really in equilibrium because we're constantly messing with them. Okay, so because we need that resolution in order to get our biological function. So what I would argue is that biological systems are more dynamic. That's what this is saying. AKA constantly changing. And this is to create biological function. So this is basically the equivalent of, like, you see this glassy pond, and what do? You throw a rock in it. That disturbs equilibrium, doesn't it? Creates those ripples, and from those ripples you get some sort of an effect. Okay, but what happens? It will go back to equilibrium, won't it? Those ripples will work themselves out, and then eventually your system will go back to the glassy pond. But you don't want the glassy pond because the ripples were what gave you what you wanted. So you throw another rock in there to keep that equilibrium going. So whenever you want that function, you toss a rock in there to disturb equilibrium, and then that gives you your biological function. That makes sense? But guess what? Here's where structure function comes in. You've got a function, disruption of equilibrium, right? But guess what you needed in order to disrupt it? Which is structure. Right, so you needed a structure to disrupt the equilibrium, which gave you your function. So you can see how function and structure goes together hand in hand. Okay. Okay, that is the end of 1. But there's no rest for the weary, because we are headlong into chapter 2. Now, chapter 2 is basically going to be our chemistry chapter. And so what we're going to be doing is we're going to be laying down some of the groundwork. So remember, we said the idea here is we want to build an organism, right? So that basically means that we need to take our big biological questions of life, that's true. And then we need to kind of assemble these things together so that we can create our biological organisms. However, before we start to build our biological organisms, we need to set our foundation. So we need to build our foundation, and it needs to be a strong foundation. In all living systems, there's actually a 2-part or a 2-layered foundation. First of all, there's 2 sets of rules. The first set of rules governs everything in the universe, all of it, living and non-living. Those are the universal laws. So those are things like the laws of gravity, for instance, the laws of thermodynamics, right? These are things and laws that are true, whether they're here on Earth or they're on the moon or they're somewhere in some far-flung corner of the galaxy that we haven't even imagined yet. Okay, these are universal laws that apply everywhere. Just, natural reality. If you're going to walk through that door, these are the rules that you subscribe to. So these are the unchanging, immutable laws of the universe. Now that forms your bottom layer. On top of that, then, are some of the laws of chemistry that define some of the behavior of some of the atoms and things of that nature. Okay. So chemistry is beholden to the laws of physics. Laws of physics are kind of their own thing. And then upon this dual foundation of physics and chemistry, then we build living organisms. So any living organism that we build has to obey and be consistent with both the laws of physics and also with the laws of chemistry. Okay, both of those govern what we can and can't do. So that being the case, then because this is not a physics class, nor will you guys likely be interested in diving deep into biophysics, which is fascinating, by the way. I'm just saying this in case you're interested. But a little outside the scope of this class, right? Now, there are some laws of physics that we will cover, and we will kind of talk about them as they weave their way into the biological system. So when we see our biological organism obeying the laws of physics, being constrained, and that is hemmed in by the laws of physics, then we'll talk about the laws of physics that are doing that, okay? So a lot of times students will be like, well, how come the cell can't do this? Well, because that'll be a violation of the laws of physics. And you can't do that, right? So so when we meet those moments, I'll unpack the law of physics that's at play there and basically illustrate how biology is having to conform to that law, okay? But most of what we do in biology is conforming to chemistry. And so let's talk about that first. And we want to first start by talking about matter. So matter is defined as mass. So anything that occupies space, that is living and non-living. So if you are alive or not, and you have volume, that is to say you're taking up space in the universe, then you are matter. Now there's two different ways that we want to describe matter that I want to sort of talk about here. We've already talked a little bit about some of these in the previous chapter. We're going to talk about atoms, and we're also going to talk about elements. Now I want to define elements, and we talk about elements a little further down in the chapter, but I like to sort of cover it here with atoms as an alternative way of talking about matter for the purposes of just the way we're going to be using it. But when you take a look at an element, any given element, there's one standard definition for the element. And that is basically an element is any substance that cannot be broken down into any other substance. It's pure. And I'm going to show you an example of what that looks like here in just a second. However, we also kind of had a little bit of a descriptor to atoms, didn't we? We kind of had that one. That was the beginning of our classification, right? The levels of organization. That was the beginning, the bottom level. Everything's made of atoms. So let's just describe atoms here from the matter point of view, right? So kind of laying this foundation. So let's take a look at an atom and sort of see what this basically is. So the atom basically is the basic unit of matter. Now that's nice, but not helpful, right? It's about as helpful as it was when I said that a cell is the basic unit of life. It's a bunch of words and I understand the individual words, but I don't really understand what the phrase means, right? What does it mean to be the basic unit of anything? It's basically a similar definition that we had for the cell, in the sense that this is the smallest that we can get and still retain the traits of the element. So let's do an example here. Okay, I'm going to do like a little gold ingot, fresh out of the mint. Got a little mint stamp right there. All right, so this isn't an alloy. This isn't a mixture. It's not 10 karat. It's not 14 karat. It's not 18 karat. This is the real McCoy. This is solid and true all the way through. Okay, and this is going to be a piece of gold. So what's the elemental symbol for gold? Anybody know? What? I heard it. Yeah. Right there. That's gold. So now here's what I want to do to illustrate this idea of the difference between the element and the atom. So if I were to cut this gold bar in half, is this top half still gold? Sure, right? If I were to cut this in half, is that top half still gold? Yep. If I were to cut this like that, is that corner still gold? Sure, keep going. If I were to cut this, is that top half still gold? Yep. Okay, let's keep going. Is that little corner still gold? Sure. If I were to take like a little smidge like that, is that still gold? Okay, now if I were to take a single atom out of that smidge, is that still gold? Yeah, the circular. I like that. I like to cover all your bases. Just the circular rotation, right? Thank you, neck muscles, right? This is usually when you get a little weight. How many of you guys say, yeah, this is still gold? How many of you guys like, no, I don't think that's gold anymore? Go about an even split. The answer is yes. This is still gold. Why? By definition, the atom is the smallest that we can get and still retain the properties or the traits of the element. What are the traits or the properties of gold? Imagine I'm blind. I've never seen gold before in my life. Describe it to me. Nobody's rich enough to have gold. Yeah, I'm with you. What? The color. What is the color? Okay, it's yellow. Yep. Go ahead. There's a few more. It's dense, right? Yep. That's what makes it heavy. Yep, it's very dense, right? Okay, keep going. Luster, right? That's a metal trait that oftentimes metals have, but that's part of its traits, right? That's a chemical trait that it has. Go ahead, keep going. You what? You can melt it. True, but even better than that, related to that. Let's see if I can tease it out of you. How? With heat, but do you need heat? Well, if you had a piece of pure gold, can you mold it without heat? How many of you guys have heard of the term gold leaf? You heard of that term? Oh, so young, so much experience necessary. So gold leaf sounds what it sounds like. Leaf, like leafy texture, that's made out of gold. It's like a thin sheet of gold. Yeah, do you need heat to do that? No. So what property of gold allows you to be able to do that? It's working off of your idea. You kind of went, so the melting is like the extreme of this idea. So you're kind of like the extreme version of that idea. What? Yeah, it's moldable. Malleability, right? Which is a thing that we see in metals. Some metals are very malleable, some are not. Gold is exceptionally so. How many of you guys are wearing pure gold right now? Pure gold. Like there's absolutely nothing in it. Not like a high percentage of gold, but like absolute every single atom in there is gold. Yeah, I know, right? It's like, what is going on here? Do I have to send this to a chemistry division to make sure that yeah? What's pure gold jewelry like to maintain? It's a nightmare. It can be, right? Because like if I were to do this to a pure gold ring, what am I looking at on my ring? Yeah, I'm looking at a big old divot, right? Why? Because of its malleability. It's super, super soft. So pure gold, the real thing, like this ring here that has, it's like one of these signet type styles, that would have been gone a long time ago. Just because of just natural like wear and tear like that, that's gone. Which is one of the reasons why I'd say probably 99% of the people out there wearing gold are wearing some sort of a gold alloy. Because pure gold, the purest gold, like nothing else, but just gold atoms in there, is so soft that it's a problem. And you literally, I mean, like what you start off with, that beautiful ring that you start off with, is just like a blob of gold chewing gum on your finger. That's what it turns into because it's so soft. And that's the reason, by the way, why they make different carats. I mean, usually if you're in the jewelry industry, you're thinking it's like, oh, well, for all those of us who are cheap, we go for the 10 karat gold, right? Because, you know, we don't have an expensive enough job to actually be able to handle the real gold, right? And so we do that sort of thing to our significant others sometimes. But see, me, I don't even have gold. I mean, this is like, you know, steel. This is like something off of my car that I have them fashion into an actual ring. So no, the reason why is not necessarily because it's like, oh, well, this is like, you know, 10 karat is gold for the poor people. It's not like that necessarily. In reality, when you're choosing a ring, a smart jeweler will say like, okay, take a look at your lifestyle. You want to go for the high end, the 24 karat, then you had better have a strategy for yourself that's going to maintain that ring. Because I can guarantee you right now, it is going to be silly putty on your hands within a short period of time. This is one of the reasons why folks who work for a living with their hands, who are carpenters, and like say, for instance, they want to wear the wedding ring, but they don't want it to just be obliterated because they're constantly, like if they're carpenters or something like that, or they're construction workers, but they want to wear that ring, they'll get the lowest carat because that is going to be the most robust to damage. So you're not going to have a lot of damage on your ring because you're working with your hand, you're beating it up all the time. You're like, so it's going to hold up the test of time. That's a 24 karat ring. Within a year of work, that carpenter's got, they basically paid a lot of money for nothing. It's not the ring you bought. Okay. That gets very frustrating for people a lot of times. But that's one of the big things. That's the reason why you make these alloys, is because it's like, listen, you're not some sort of a rich aristocrat and all you do is just sort of lay around on a lounger all day long, ordering your servants to feed you grapes, right? I mean, if that's the case, you can be draped in pure gold, doesn't matter. But if you're like a normal person and you actually work for a living, you're going to have just daily wear and tear on you and your body and your jewelry, which is why you go for the lower carat, so that it can actually be more robust. Okay. Yeah, granted, the 24 karat looks great because it's a darker, truer gold color, but you pay a price for that. So I know a lot of people that are like, yeah, I got a really beautiful ring, but I can't wear it. So what's the point of having it? I mean, just have the thing melted down and turn it into a little gold ingot then. I mean, that's because that's about as useful, right? So no, it's still gold, right? But now we're at the atom and it's still gold. So let's go ahead and blow this one up. Is that still gold now? How many of you guys say yes? Okay, a couple. You blew the atom up. Yep. So how many of you guys say no? Okay, so a little more confident in no. The answer is no. Here's why. Because now what you have is basically atomic guts. That's what you got. We can do the same experiment with just us, right? So if I were to cut, so you guys are a room full of 1111 students, yes? With all the attributes and properties of an 1111 student. Now, if I were to cut this room in half, right down here, and I were to pick this half, are you half right here? Are you guys still 1111 students? Sure you are. Now, if I were to cut you guys in half, are you guys still 1111 students? Sure, right? So if I were to cut right here now, I'm going to pick on you, right? Are you still 1111 student? Yeah, right? With all the traits and the attributes and the properties of an 1111 student. Now, if I were to tear off your arms and your legs and your head and put them all in separate piles, are you still now an 1111 student? No, right? Because your arms no longer retain the properties of an 1111 student. That's as far as you can go. So we would argue that you as an individual is the smallest you can get and still retain all the properties of an 1111 student. Same thing here. After I tear your arms and legs off, you basically become a pile of body parts. Right? So the same thing is also true for the atom. Right? So if you basically break the atom up into its constituent parts, its subatomic particles, then what you've got is a bunch of atomic guts, so atomic body parts. That's what you've got. But you don't have the functional element anymore. Now, let's take a look at the atomic structure. First of all, in an atom, we have two main regions of an atom that we're going to be taking a look at. The first region is in the center of the atom, that's the nucleus, and the other one is going to be around the nucleus, which is the electron cloud. There's a couple of particles in each of these. First of all, we're going to take a look at the protons. Protons are a particle that you're going to find in the nucleus. These guys are basically large, they have a large mass. They are positively charged particles, and we typically will abbreviate them as P+. And so we're going to write a couple of particles here in my nucleus. So there's 3 different protons there. And so they're going to be in the nucleus. Now, the other particle that's in the nucleus as well are the neutrons. These are also large in mass. They have neutral particles. That is to say, they're no charge. And they are going to be N0. So I'm going to add some neutrons in there. There's one, and then there's one. I'm going to put a slash through them to designate there's no charge there. And so this is your nucleus now, composed of largely positive and no charge particles that are both large in mass. Now, the other part of the nucleus in the cloud are the electrons. So the electrons themselves, size-wise, are vanishingly small. They're negatively charged, so we tend to abbreviate them as E negative. Okay. Now, here's the thing. When I say the term vanishingly, and this is actually a term that my intro chemistry teacher once used on me, and he was kind of an expressive guy, so I was trying to figure out, it's like, okay, wait a minute, is that actually a discrete descriptor of them, or is that just you kind of being theatrical? You know, it's like, why vanishingly? And in this particular case, he said, even though he was theatrical, he said, no, in this case, it's actually an accurate term that I want you guys to understand and imagine. And he told me this. He said, imagine this. Imagine it. Electrons are so small, so tiny. It's like they're vanishingly small. What does it mean to be vanishing? You can barely see it. They're in danger, aren't they? It's like they're vanishingly. It's an adverb for vanish. It's like it's an ad, which means it's describing something, right? So what you're saying is you're not just small, which is an adjective. This one is an adverb, which means it's actually in the process of vanishing. It's like it's so tiny, it's almost as if it is literally like milliseconds away from literally just waking out of existence. It's so tiny, okay? And that's the way he wanted me to remember it, is that it's so vanishingly small. And so typically, these guys will inhabit spaces around the electron cloud called orbitals. And then they will just basically be out here whizzing around the nucleus in the electron cloud in these orbital-like structures. Look familiar? Kind of looks like your basic atom, right? What you see like on the little NASA thing, right? Where you see the little electrons around the atom. So those are your two main regions. You've got your nucleus and you've got your electrons sort of whizzing around. Now, what we see here are two different representations of this idea, the nucleus and the electron cloud. One of these is more accurate. So for instance, this one up here is a spatial representation of electrons that are in space, that is at a given point in time. And so typically what you have, like for instance, you have hydrogen, which has one proton and one electron. And so you have this one proton in your nucleus, and then your electron in this particular model is actually inhabiting electron cloud. So this electron cloud here is actually a statistical region where the electron will inhabit. And so this is what it looks like. So you have that one electron, right, whizzing around in there. And the idea is as it's whizzing around, if I stop and freeze frame, then that electron will be somewhere in that cloud, that yellow statistical range, okay? Now, if I start it again, it's going to be whizzing around somewhere in that yellow fog bank. And then if I stop it again, it'll be maybe somewhere else. So it'll be there maybe. And if I let it go again, it'll kind of keep going. And then if I keep stopping, it just kind of keeps stopping wherever. It's going to be in different areas, but it's always going to be in that statistical area, in that yellow fog bank. Okay, that's the electron cloud. Here's an example of an oxygen where you have 8 protons, 8 neutrons, and then 8 electrons. So here you can see all your positives here. And you have these 8 electrons now, which are just basically whizzing around in this electron cloud. And so at any given place, they're going to be in that particular cloud. And it's all random, right? So where they are in there is just completely random. So they're just like ping-ponging around, just pinging around in there. And they're just kind of zipping around. So the reason why I say that is because we want to compare that to this one. This is the Bohr model. And the Bohr model is basically a diagrammatic representation of the personalities of the electrons. It's not real life. Okay. We used to think it was real life, but it's not real life anymore. And here's how the Bohr model works. And this was basically created by Niels Bohr, who won the Nobel Prize. So he was a chemist back in the 20s, 30s, 40s, and he was a really smart guy. Won the Nobel Prize, but this was this is how we thought things worked back in the day. So we had this imagination that here you had in the nucleus particles, protons, neutrons in the nucleus, very similar to the way the sun is sort of in the center of our galaxy. It's actually not in the center of our galaxy, but in our solar system, right? And then around this orbited these particles, electrons, in a very definable orbit, very similar to the way the planets can very definably orbit the sun, okay? And as a matter of fact, we used to think it was very similar, but actually we used to think it was galactic in nature. Now, what can you do with a galactic orbit? Because the galactic orbit is basically linear velocity that's been captured by gravity. So that's the reason why it curves and it's going around the sun, because it's captured by the sun's gravity. And so it becomes non-linear. Then we actually have equations in astronomy where we can predict the orbit of any given body that's orbiting the sun, right? And we can do that with physics, with just basic physics. It's not a very difficult calculation. So like, for instance, if we wanted to predict where is Jupiter going to be in its orbit 6 months from now, we could do that because we've got calculations that can allow us to do that. So the idea of a galactic orbit has a great deal of predictive value to it, okay? We can calculate it all out. Matter of fact, if we wanted to, I mean, barring any great catastrophe, we could probably calculate where Jupiter's going to be in its orbit 20, 30, 40, 50 years from now in June, right? Because it is predictable and calculable, okay? And that's the way we used to think in the Bohr model. However, what we realized is that's actually not the case. Why? Because the orbit of an electron in the cloud is not calculable and intentional the way the planets are around the sun. It is random. So movement of the electrons is random and erratic. So we can't calculate where an electron is going to be at any given point in the cloud. Okay, we try, and so that calculation breaks down. Okay, so now we know that the Bohr model doesn't work. That's not it. Matter of fact, if you guys take Dr. Dillman for chemistry, he's probably screeching right now because it's like, you're teaching the Bohr model. No, it's like, okay, so we're not like chemistry. They don't teach the Bohr model because it's wrong. It's this one here, right? This is the one that we've generated from all of our understanding and our learning from quantum mechanics, right? The way particles are moving in space. And so that's what's led us to this one. This is a more accurate term. And so the Bohr model has been done away with. But in biology, we're not teaching it because we're saying like, aha, the Bohr model, that's the way it is. We're wrong, but that's the way it is. Right? That's not what we're doing. So with the Bohr model, notice the emphasis here is diagrammatic. We're simply using the Bohr model to help us schematically lay out and organize the differences between electrons. Okay, so it's a visual tool for us to be able to understand the different temperaments and the different types of electrons that we have. Because for us in biology, we really want to look at the electrons. That's what we want to focus on. And we're going to move in there. But before we get there, we have to do a little bit of work on the nucleus first, and then we'll shift our attention to the electrons. But you can see here, if you've got more electrons, you can sort of arrange them in these rings, and we'll build one of these a little later on in the chapter. But that's the Bohr model. So the other thing is atomic number and information about a symbol. So let's take a look at this. And what I'm going to do is I'm going to insert a slide. And what I want to do is I want to go over something here as an aside, because we've got some physical information associated with elemental symbols. And I always like to do this for every single class that I have, because a lot of times what happens in chemistry, and to a lesser extent in biology, is in chemistry, the chemists, they start to just write stuff, equations, and they're putting numbers all over the place and all that sort of stuff. And a lot of times they just kind of assume you're along for the ride, right? And then you're like, why did you put a 2 up there instead of down there? Or what does it mean when the 2 is up and not down, right? Or something like that. And so a lot of times they just assume you're kind of along for the ride, and that may or may not be the case. And so one of the things I want to do for you is kind of put all the information that we have for an elemental symbol in one place, so you can kind of have a little bit of a decoder, so you know exactly what we're talking about whenever you see a number in a particular position. This is something that I had to learn the hard way when I first took chem way back. Because I had one of those teachers that was like, they would write a whole bunch of notes with their right hand, and then they would like erase with their left. And then of course they're writing all these numbers all over the place. And I'm like, wait a minute. So what does it mean when you write a 2 right there? And I would like struggle for a while and like for weeks. And it would take me like a couple of weeks to figure out what that actually meant. But by that time, everything else just kept coming. So it's like you didn't really have a good handle on this one, and they kept throwing you stuff. So you're like, okay, got this one, but I'm still kind of juggling this one over here, right? And so it was just, that didn't go well, right? So, by the time I figured out what they were writing, I had already been, 2 or 3 weeks behind. You could imagine that semester did not go well for me. So what I want to do is decode this. So I'm going to take a look at an elemental symbol X, and there's going to be 4 positions of information. I'm going to start off with number 1. Number 1, that is down here in the lower left-hand corner. If you see a number in there, it's basically your atomic number, which is essentially the number of protons. And it defines your atomic ID, your atomic identity. Now, at this particular point, I like to do a little bit of illustration here for you guys. So I'm going to take a look at this one right here. On the periodic table, you see C. What is C? Yeah, it's carbon, right? So how many protons does carbon have? Generally speaking, that number will be on every periodic table. It's usually above your elemental symbol. It's either directly above, centered, or it's usually to the upper right-hand corner. Very infrequently, it's in the upper left-hand corner because there's other information that goes there. But what is the atomic number of carbon? 6. Okay. So here's an example of your atomic identity. Okay. So carbon has 6 protons, yes? Okay, what happens if I add a proton? Am I still carbon? Well, if I add a proton, just stick with that one. If I add 1 proton to carbon, which has 6 now, am I still carbon? What have I become? Yes, right? Because nitrogen has 7 protons. If I take a proton away from carbon, am I still carbon? What have I become? You're thinking whatever B is, right? Boron, right? So I cannot change the number of protons I have and without me becoming something different. Think about your own identity number, right? Your S number, perhaps. If you were to change your S number by 1 digit, does CCD recognize who you are anymore? Nope, right? So that's your identity for the purposes of your business with CCD. Same thing is also true here. The number of protons is your identity. You change your protons, you will change who you are. Now, the important thing is, generally speaking in nature, most atoms do not want to change their identity. They do not want to do that. So there's only one case where they do change their identity, and that's when they're really unstable and really unhappy. So if you run yourself into a situation where it's like, you know what, it's better for me to be somebody else and stable, than for me to be who I am and horribly, horribly unstable. Okay, that's the one moment when an atom will be willing to change its identity. And we'll take a look at an example of that in just a little bit. So this is basically your atomic identity. Now in position number 2, you have your atomic mass, which is the number of protons plus neutrons. So that mass number will be in number 2. Generally speaking, on the periodic table, that mass will be underneath the elemental symbol. So you'll see it actually under here. So you can see the red. So it's going to be underneath. This will be your mass. That's what that squiggly line is. Right. So those are your atomic masses. So it's protons plus neutrons. Why not electrons? Well, they don't really vary so much. They're all largely the same mass, same charge. What? They're vanishingly small, right? So if I were to take an atom and ask you, tell me what the mass of that is, you would only do it. It's like, it'd be like me saying, go out and get a watermelon out of the watermelon patch and tell me how much it weighs. Would you tell me and account for all the dust that's on it? No, why? Because it's negligible, right? It doesn't even register. It's the same thing. This is like an atomic watermelon, and electrons are like the dust that's on it. So like 99.999999999999999999999% of the weight is protons and neutrons, right? So that's the mass number. So you'll see that here. So for instance, you'll have carbon 6 with 6 protons and a mass of 12, right? So that's what we have for carbon. Sometimes you'll also hear it referred to as written out. So this is carbon 12, and then there's carbon 13, and then carbon 14. Those are mass numbers that we have there, okay? Generally speaking, you don't see this used a lot unless you're working in nuclear chemistry. And they're working with isotopes. Exactly. We'll talk, and we'll define what isotopes are here in just a second. So in position number 3, this is basically your charge on an ion. This is when the number of protons is not equal to the number of neutrons, excuse me, electrons. So now, when you take a look at the periodic table basically is a list of both natural and non-natural, synthesized, but the first 90 to 92-ish or so elements are naturally occurring. As they occur on the periodic table, they're always given as neutral. It's always assumed neutrality. Okay, what does that mean? That means for every positive charge you have from the protons, you have an equal number of electrons, right? Which is negative charge. So if I were to ask you, let's take a look at sodium. How many protons does it have? 11, right? How many electrons does it have? Right, because it's neutral. Okay. Now, what happens if it has a disparity between that the protons and electrons are not equal? Well, what that means is then you're going to start picking up a charge on your ion. And typically speaking, you will have either a -3, -2, -1, 0 if you have no charge, +1, +2, or +3. Now, on this side, what this basically means is that the number of electrons is greater than your number of protons. On this side, it means that your number of electrons is less than your number of protons. And right here in the middle, they're equal. So here's my question to you. How do you get a positive ion? You do what? You're losing an electron, right? How many of you guys are tempted to add a proton? That's a common temptation, by the way. Remember, our brains are additive in nature, right? If you have more positive charge, then how do you get positive charge? By adding more positive charge, right? Does it make sense? Only remember, if you're tempted to add a proton, remember what number 1 told us. You want to add a proton, there's consequences, right? Assuming you want to stay what you are, can you add a proton? Can you take a proton away? No. So what's your only recourse? Electrons, right? You can add or take away electrons. That's it. Okay. So if you take away electrons here, you get positive charge, right? If you add electrons here, you get negative charge. But notice what you never do. You never add or take away protons because that would change who you are. And assuming you're okay with yourself, right, you don't want to add or take away electrons. And so what that means then is that a lot of times sodium will acquire a +1 charge. Phosphate is typically -3, and so forth. So the charge number up there is the charge. So it's creating an ion. Now, number 4, and the last one, is going to be the number of atoms in a molecule. So here's a good example, C6H12O6. Anybody know what that is? I heard it both times. I heard somebody say muttered glucose and then carbohydrate, which is what glucose is. So this is one molecule of glucose. There's a couple of other things it could be. We'll talk about that later. But we're in position 4 basically says that in the 4th position, that's say in one molecule of glucose, how many carbons do I have? 6. How many hydrogens do I have? And how many oxygens? So this is the number of atoms of oxygen, carbon, and hydrogen in one molecule of glucose. Okay, that's what position number 4 is telling you. And so this is basically what you see chemists writing all the time around these elemental symbols. And sometimes we kind of get lost. We're like, oh, wait a minute, what does it mean when you put a -3 up there or a -2 or, when you put, 14 on that position number 2 or something like that. So sometimes they can just sort of rattle on and they just assume that we're there. And we're like, so wait, so I'm not there, right? So, right. And so that's basically what we have. Right. So one of the things, so we already talked a little bit about mass, the difference between mass and weight. This is very simple. Some of you guys probably already hit this, some not. Remember, mass and weight are not the same thing, but we oftentimes use them interchangeably in chemistry. So we'll say atomic mass, atomic weight. We mean the same thing. But technically speaking, they're not the same thing. Right. Your mass is how much of your matter there is taking up space. Right. That's your mass per a given unit, per a given the amount of stuff, right, that you have. So you have more mass, you have more stuff. And that doesn't change. Weight is basically your mass in gravity. So this is basically your mass times gravity. So when you say I go to the moon and I weigh less, that's your weight, right? Because the gravitational field of the moon is different than it is here on Earth. So your weight changes, but your mass does not change. And that's always something to keep in mind because all of our biological organisms here on Earth have been adapted to our reality. What is our reality? Well, the first one from physics is our gravitational field. So everything about us is adapted to this gravitational field, which is actually one of the problems with spaceflight. Because what we're doing is we're proposing to send an organism, us, into an environment that our bodies are not adapted to be in, right? And it doesn't seem like it's that big of a deal. Oh, so gravity makes you a little heavier. Actually, if you dig into physiology a bit more, your body has wired all of its minutiae, its physiology and its anatomy in response to gravity. So a lot of what you are as an organism has been adapted within that gravitational piece. Now, if you go out into weightlessness, into space, all that's off, and then all that kind of just sort of throws your whole body for a loop. And that's really what's keeping us from going to Mars, actually, is because we're not quite sure how functional we're going to be if we send ourselves into weightlessness for a long period of time, because our bodies are not designed to be in weightlessness. Okay. The other thing I want to draw your attention to is this concept of a Dalton. This is just a dude named Dalton. And so one of the things with the mass and massing out these particles is it's always tricky, right? Because we can't take a proton and put it on a scale and say, aha, you're X number of grams, right? So we can't do that because a proton is subatomic. So what we have really are relative scales. So we know a proton is big, but the question is, what is everything else relative to the proton? And that's kind of what we've done with mass at that level. One of the things we did was we basically said that let's just put a dude's name on it. Let's take a proton, which is roughly the same size as a neutron. And let's just say that that's our base unit, right? Our relative reference point. So we're going to refer everything and reference everything relatively to that size. And we're going to call that a Dalton. So everything's either going to be bigger than a Dalton if it's bigger than a proton or neutron, or it's going to be smaller than a Dalton if it's smaller than a proton or neutron. So it's relative, right? Because we don't have the capacity to discretely measure the mass of a proton. We just know it's really tiny. And so you'll see that actually in chemistry, we don't really use that a whole lot. We use other denominations. One other denomination is very similar, the same idea is what's called an atomic mass unit. Sometimes we run into that one, AMU. And so one proton is defined as one. That's our reference line. And then everything else is relative to that. So like one proton is one AMU. A neutron is one AMU because it's equal in size. An electron would be like a fraction of an AMU because it's tiny, much tinier than a proton. And so that's kind of what we sort of did with this sort of subatomic bit. Now that we've got like super colliders and stuff like that, we can do a much better job. So we can actually get down to that whole grams point where it says protons. But we still use Daltons in biochemistry. So we don't use a lot in chemistry, we use in biochemistry, especially in protein biochemistry, where we basically refer to our proteins as being like, oh, this is a protein of 53 kilodaltons or something like that, because we don't have a metric for its mass for protein. So you'll see that in biochem. So let's take a look at electrons. I want to finish with this slide. And then what I want to do is I want to start with this one next time, because this is going to start moving a little bit more toward the direction we want to go. So electrons, we already talked a little bit about the charged particles. Remember, this is a situation where the number of protons and electrons are not the same. So in cases where you have more protons than electrons, you're going to have a net positive charge. Oftentimes we refer to this as what's referred to as a cation. And then if you have fewer protons than electrons, then you are going to have a net negative charge, right? And this is what we refer to this as an anion. And the way I remember that is cat, and this is just a nerdy thing, calcium. So Ca, and calcium is one of those ions that forms a 2+ charge. It's a positive charge on it. So calcium for cation, because cation, this is always a positive 2 charge. And then for anion, I remember N for negative is a negative 1. So none of that, but N anything is a negative, right? So so anion means it's a 0 ion is what that actually means. That term means it's like a nothing ion. And so you see these terms enough to where you want to know them. We don't usually use them a lot in biology, honestly. We tend to say, like, listen, if you know that calcium is a positive 2 ion, then talk about calcium as a positive 2 ion. Right? If you know sodium is a +1 ion, then talk about sodium as a +1 ion. Don't talk about like the anion does this. Now in chemistry, you do that a lot, right? Because you're basically talking more about general principles. So like any positive ion will behave with any this in some sort of a chemical process, right? So we're not interested in general reactions like that. We want to know specifically what is sodium doing when it's interacting with this, okay? So we tend to use these terms less often than us. The other thing I want to sort of sketch out in this one is the concept of orbitals. So in orbitals, these are basically like neighborhoods within the electron cloud. Within which electrons inhabit. So when we're looking at the electron cloud, it looked like it was just haphazard, but in reality, within that overall cloud, there's actually orbitals, which are like little neighborhoods with where different electrons will inhabit. Think of it very much like this. All of you guys may not. Let's just say we're all Denverites. Let's say we all live in the city limits of Denver. Denver has a halo population. Matter of fact, if I were to take a look at where you are at any given point in Denver, you could probably draw a statistical likelihood, an electron cloud, of where you would be at any given point in the city. Yes. However, you're not likely going to end up in some places more than others, right? So, for instance, we kind of have a corridor of existence. We can kind of think of this in terms of how we live. Even though there's like this sort of population cloud around Denver, it's not like every individual is going to be in any part of that cloud at any one time, right? You live in neighborhoods within Denver. And in those neighborhoods, that's where you're going to be found. You're not going to be found in some far-flung other area of the city where you don't live or play or do whatever else you do, right? So you're going to be found in your neighborhood, but you could be found in any particular area in that neighborhood. And that neighborhood defines where you are at any given point. Now, can you go anywhere in the city you want? Yeah, but you don't, because you typically just focus on the areas you need to go to, right? That's largely where you go. And that's what orbitals are like. Orbitals are like these individual neighborhoods within which individual electrons will sort of hang out within the context of the overall electron cloud. And so those orbitals are an important concept because they will help us frame a little later on our concept and organization as we start to organize the differences between our electrons and start to understand their function, what they give us as we go down the slides. This will help to kind of organize them into their little neighborhoods, right? So different people in different neighborhoods have different temperaments and different personalities. Okay. Does that make sense? Okay, so we will start with isotopes next time.